So we're starting on absolute motion analysis now. And we're not going to put much time into this relative to the course. It's basically an exercise in some geometry. So what I have here is a cam follower mechanism. So this is a cam. It's in the shape of a circle. And what I have here is a spring-loaded follower. So this spring here forces this to stay in contact with this as it goes around. And so we have, relative to the center, the geographical center of the cam, I have set up my XY axis. But note that the cam, if we had this rotating around here, it'd be really boring, because if this was pinned here and it's just rotating, this thing would never move because the radius is constant. So what's happening here is we've actually pinned it at the outer edge of the circle. All right, and so this thing then would rotate like so. Okay, and that'll make this follower kind of go in and out, like that way. Okay, you have a lot of courses that follow up this course, one of which is kinematics, which you would nominally be taking in the winter term if you took this in the fall term. This is the kind of thing that kinematics will put your kinematics course, which follows, will put a lot of time into. So this won't be a big focus for us. Anyway, so if we look at this problem, it's all geometry. So it's pinned here. So as it rotates around, off of the horizontal, we'll measure theta in the usual way. The geographic center of this cam is at the center of the circle. So that'll be from here to there is a radius r. No mystery. And we're to the point where this comes into contact, that'd be r as well. So we have this follower is lined up with the point of rotation, so that you can see this line going across here in red. All right. So what's an equation for if I wanted to say where the follower was? I could simply measure this distance L off of this point. All right. So from here to there, right here, that would be pi. So if I look at this angle right in here, that angle would be pi minus theta. So pi minus theta, if I was to say r cosine of pi minus theta, I'd have this distance right there. Well, this distance here is just the same thing. So it's 2 times that. So I can write the following. L, this distance off of O, is, and I'll take, if this is positive, then going back would be negative. So minus 2r cos pi minus theta. Now if you use your trig identities and stuff and expand that thing out, you wind up with a cos pi, that's a minus 1, and the sine pi is 0. Okay. And so now we're just left with 2r cosine of theta as it all reduces down. Take the derivative, you would have velocity. Take the second derivative, you would have acceleration. Now, oftentimes when you do these problems, as something moves, the equations actually don't fit. So we will note that this equation is only valid from pi over 2, so when this point is up here, to when it rotates down to there. Okay, so this center will go like so. Once this goes to the other side, you'd need a new equation. Okay, so only valid over a certain range, typical of these kinds of problems. That's not terribly unusual. All right, we have another set of absolute motion analysis problems, and these are the kinds we're going to see more of during the semester, during this course. And that involves pulleys. Okay, we've seen a little bit of pulleys already. But let's take a look at this set here. So I have compound pulleys here. And so we're going to make an assumption. You'll see the assumption is right here. I'm going to assume that these things are significantly far enough apart that we can consider all the ropes to be parallel. Otherwise, you have to figure out all of this geometry, and that would be really quite involved. So if these are sufficiently far apart, they would be, even if you looked at them, they would So picture you have for reasonable sized pulleys, and these are 3-4 meters apart or something. They would look pretty parallel. All right. So as always, when we handle pulleys, we're going to write an equation, set it that we can set equal to a constant. So we're just going to be concerned with the dimensions that can change as opposed to those that can't change. What can't change? The rope going around the pulley at any given time is always the same, unless you are basically unwrapping the pulley, in which case everything's collapsing. So that's we're not going to be concerned with that. So what do we have? We have, if these are all parallel, I've got 4 ropes going from here down to there. And so I'm calling that, so here's A, here's B, 4xAB, and then the amount of rope I'm pulling off, I'm calling X. So whatever rope I pull off of, it comes out of those 4 ropes there, or sections of rope. Okay? So we have X plus 4xAB equals this constant. All right? Well, take the derivative, and we wind up with the velocity, which we pull this thing off, so that's supposed to be given, is minus 4xAB, or this velocity here is minus 1/4. So as this goes down, that's going up at 1/4 the rate. One more of these. So here I have another pulley system. So what's going on? I've got 3 pulleys that are dangling down. This one dangles down directly from the ceiling. I'm measuring off of this point, and we're pulling off this rope at 2 meters per second here. That's what we're given right here. And this goes up and around C, and back up. Okay? So there's one rope, and then if we look carefully, we'll see there's a second rope. And that one goes around here and deals, basically it's suspended between the ceiling and pulley C, and this is our other pulley. All right. So for this one, we simply need 2 equations which describe the parts of the rope that change. So if I look at this rope, all right, I'm pulling off XA. So however much I pull off here, and that's going to come out between here and there. All right, and so I'm going to call XC this distance from here or here to there, where the pulley starts to do its wrapping portion. All right, so for this rope, I have XA that I pull off plus 2XC. I don't care about this portion because it's constant. It's boring. It's just from here to here and there to there that can change. Take the derivative, and you get VA equals minus 2VC. Now I have this rope. And so if we look at this, this one can be confusing. You're like, what's this distance from here to there? Well, it's nothing more than this distance down to B, XB, minus this distance here would give you what's here. So that would be XB minus XC. And then the distance down from there is XB. So we have 2XB minus XC in here equals C2. Take the derivative. 2VB equals VC, solve, and we get, knowing A, VB is minus 1/2 meter per second. So as you pull this down, this goes up. That's what we'd expect. So that finishes up what we're going to do on absolute motion analysis. We will now, next video, we'll begin looking at instant centers.